So before we launch into analyzing circuits and talking about how to power things and how much current flows through particular objects, we're going to have to go through the basic ideas of electricity, how it works, and then we'll have to talk about a thing called Ohm's Law, which is the underlying theory behind all direct current appliances. So we'll start off with the things that you need to, like the words you need to know in order to talk about electricity. So the first off is resistance. So resistance is measured in a unit called ohms. You've maybe seen that before. It's one that you've seen certainly on appliances. Ohms. And they're represented by an omega. So you can see it's Ohm's Law, it's going to have something to do with resistance. So resistance, this particular feature, is a property of a device that you put on something or of a material. So let me try and write this while I talk at the same time. Resistance is a property of a piece of equipment or material and what it's measuring for you is it's giving you a number to represent how hard it is to push electrons through that particular material, or how challenging it is for the energy conversion process between electrical energy and light, or electrical energy and heat, whatever the machine is doing. So a property of a piece of equipment or material, and measures how difficult it is to drive current through that material or object. How difficult to drive current. So if you go and you look at things that you can buy, like speakers or light bulbs, they don't quote you a voltage, right? Like they don't say it's a 9-volt light bulb. They'd say it was a 9-watt light bulb. So that's it's not resistance anyway. And on a speaker, you'll find that the resistance is quoted in ohms. And if you look at the back panel of any piece of electronics, that this is the property of a device that you're going to wire into your circuit. So the next thing that happens in a circuit is once you have the stuff that's going to absorb the energy, you have to have a source to provide it. So voltage is the property of the source. So voltage is measured in volts, not terribly creative, which are represented by a giant V. And so voltage is a property of your electron source. So you would say that a battery is a 9-volt battery, or that the household current available in your house operates at 110 volts. Well, that has something to do with how those electrons are energized in the first place. So, for example, batteries, like an electrochemical cell, produces 1.5 volts of voltage or electrical potential. So if you need a 9-volt battery, you have to have six little batteries on the inside, and this is not recommended. Don't do this at home. But were you to cut the top off of one of those square 9-volt batteries, you would find 6 little mini batteries tucked inside of it. And if you've ever seen a car battery cut in half, right, they operate at 12 volts. So each of those cells at 1.5, what does that take? Like 8 cells, so 8 little batteries inside, each operating at 1.5 volts, produces the 12 volts that you need to start your car in the morning. So this has nothing to do with the devices you're running, right? It's not the computer that you're running or the light bulbs that you're trying to turn on. That's this, right? Light bulbs have resistance. Computers have resistance. Batteries provide voltage. The Bruce Nuclear Power Facility provides voltage. And then the third one that goes up here is current. And it is measured in amperes or amps. And it's represented by a big A as its unit. Current is a consequence of these two things. If you have a power source providing a certain amount of voltage, and you have an object receiving that energy with a certain amount of resistance, these two features together will determine how much current flows through that circuit. So let me jot that in there. Is determined by the combination of resistance and voltage in a circuit. I can't talk and write at the same time. Okay. So if you put a high voltage on a low resistance circuit, then you're going to get a huge amount of current happening. If you put a low amount of voltage on a high resistance circuit, you're going to get very little current flowing. So this thing here is sort of a consequence of the combination of pieces that you attach to your machine. All right. So the last one then is power, which we've dealt with before. And power is measured in watts. Which is represented by a big W as its unit. And power is the amount of energy transferred per second. You're all going to fact check my spelling of transferred there. Okay. So with these 4 quantities up on the board, we can do a little. We can write Ohm's law. So Ohm's law for DC circuits is that the voltage you apply is equal to the current that's generated multiplied by the resistance of all of the things added up in the circuit. So it's not a terribly complicated equation, right? If you know the resistance of the object you're plugging in, and you know the voltage capacity of the electron source that you're using, then you can easily calculate the current that will flow through it by dividing this by this. I think we had done earlier that the power for an electrical circuit was the current that flows multiplied by the voltage. And so you should sort of see that, right? If this is the energy density or the energy available from your battery or from your power plant, and then you let lots of it flow, that's going to increase the amount of energy that's transferred per second. So bigger this means bigger that. If you have a lower voltage, then you're going to have a lower power. If you have a huge resistance and a small voltage, which leads to a small current being driven, then there's not much flow, so the power is less. And these things are all interconnected. So I'm going to erase all this stuff, and we're going to try just a quick little example of how to do some calculations. So, based on Ohm's laws and the power equation there, how much current will flow if you connect a 10 ohm resistor to a 12 volt battery? Well, I have this thing in ohms there, so that's a resistance, and that's a property of this thing. This 10 ohm resistor could be a radio, could be a light bulb, it could be your toaster, whatever it is, it's providing 10 ohms of resistance to the circuit. And I have this thing here measured in volts, so that's a voltage. And I've been asked for current. So current is the I in all of my equations. So I'm just going to take Ohm's law there. I'm going to write her down. And if I put the 12 in here, I don't know. Resistance is 10. Then to get my current, I'm just going to have to divide both sides by 10. And current is measured in amps. So 1.2 amps is going to flow. Now in the spirit of just finding out everything you can, I know how much current is flowing now, and I know how much voltage is being applied. So once I know those two things, I can get power so that I have all four variables accounted for. So if I start off with that power equation, the power would be the 1.2 amps I just calculated, and then the 12 volts. And 1.2 times 12 is 14.4 watts. So if you think about the old incandescent light bulb, right, the ones that look like a filament inside a glass bulb, like so. If you look those up at the store, if you can still find one, they didn't come in sizes much smaller than 60 watts. And if you had a 60 watt light bulb, it was like mood lighting, not terribly bright. If you wanted to light up a whole room with only one or two bulbs, you needed a 100 watt bulb, which is much higher than this. This rating, 14.4 watts, that's getting closer to what the LED bulbs are operating at now. So this 10 ohms of resistance, that might be about right for an LED bulb that's operating on a battery pack, approximately. All right, good. So I'm going to erase this, and then we'll try another example. So if you had a device that offered 60 ohms of resistance and you were trying to drive 3 amps of current through it for whatever reason, how much voltage would you have to apply? So what type of power source would be required? Like what process would be necessary in order to make this much current go through that much resistance? Well, again, I mean, that's, you just circle your things there. Like this is a current and this is a resistance. So in my Ohm's law, we just write that out. Voltage is current times resistance. This I don't know, it's asked me for it. Current is 3. Resistance is 60. And so that's going to give me a total of 180 volts. I like to write volts at the end so that I don't confuse V, the variable, with V, the unit. It's up to you if you want to do that. So again, in the spirit of completeness, we should grab that power equation and see how much power this thing is consuming. So power is current times voltage. So 3 amps of current operating at this voltage Oh, 300, 540. So if 3 amps of current are flowing through this machine that provides 60 ohms of resistance, then that machine is absorbing 540 watts of power. So 540 joules per second are being consumed by that machine, which means that your power source has to be providing 540 joules per second. Okay, so I'm going to erase it and then do one more example, and then I think it's off to the practice problem. So back to that 100-watt light bulb. It seems to be the workhorse of early electrical calculations. Now we're going to assume that this is a DC circuit, which is not true, but whatever. How much resistance is provided by a 100-watt light bulb operating on a household current of 110 volts? Well, this thing here, that's a power. That's listed in watts. And this thing here, that's a voltage. So instead of starting with my Ohm's law, I'm going to start with a power calculation instead. So power equals current times voltage. So 100 watts is, I don't know the current, but I know that the voltage is 110. So I just have to divide 100 by 110 in order to get the current. The 1/11th is like 0.99999, I think. 0.09999. Etc. Amps. Okay. So this process, whatever's happening between your power plant and your house, is delivering electricity that provides this kind of energy. So that's the energy. We'll talk about that in a second. This is sort of how much energy is being, the intensity of the electricity that's coming out. That's a good word. The intensity of it. In order to shed 100 joules per second of light and heat and whatever else is wasted in that light bulb, at this level of intensity, that bulb has to be receiving 0.9 amps worth of current. So if it's receiving that much current at this much voltage, then I should be able to calculate the resistance there using my Ohm's law. So 110 volts is 0.9090 repeated multiplied by the resistance. So I just have to divide this by this. And if you have kept all of the digits in your calculator display, you end up with 121 ohms. Lovely. So that light bulb, if you're plugging it into a circuit operating at this voltage, and it's that flavor of light bulb that sheds 100 watts of light or heat, then it must be drawing 0.9 amps of current, and the bulb itself is providing 121 ohms worth of resistance. Okay, so I'm just going to erase that and then maybe do a little summary of what these things are now that we've done a few calculations. All right, so I'm going to start with this energy or this power equation here. So power, as we said on the first board, was measured in watts, and the definition of a watt is a joule per second. So 1 watt is 1 joule per second. And that power is equated to your current times your voltage. So if I take current then, and it said that it was measured in amps. I need to get, well, hold on, let me finish this then. And then I've got voltage up here. Voltage was in volts. When I multiply amps by voltage, I have to get watts, which means if I multiply amps by voltage, I have to get joules per second. So I need a per second in one of these two units. So I need one of them that's counting something that's happening over time. Now this thing isn't doing that, right? Like a battery isn't doing anything over time. It's just, it has a chemical reaction that has this particular ability to deliver energy. But current, if you use that word outside of electricity, like in a river, right? Current is how much water goes by per second. So a high current has lots of water go by in a second, and low current has not very much water per second. That's where my time dependency comes in. So this amps, the definition of that is what's called a Coulomb per second. Now, Coulomb is it's counting the number of charges. So it's the same way as when you go to the grocery store, you buy a dozen eggs. There's just a word for that. There's a dozen, means 12. Coulomb is a certain size of bucket of electrons. So, and it's a lot, right? It's millions and billions and trillions of electrons in one Coulomb. But it's measuring how many of those packets go by per second. So this one then, if I'm supposed to multiply this by this in order to get that, I have the seconds in the bottom. I don't have the joules in the top yet. So this thing is going to have a joules up top. And when I introduced this one, I ended up with a Coulomb on top that I didn't want. So I'm going to put a Coulomb in the bottom here to cancel it out. So that if I took coulombs per second and I multiplied it, right, like coulombs per second, and I multiply it by joules per coulomb, then these undo each other, and I'm left with joules per second, which is power. This was current. This was voltage. So that works out tidily. But what does this mean? Right, question mark. Joules per coulomb. Well, if you think about that, when a battery is working, it has electrons coming in one end and coming out the other. So it's doing that in well, you can measure it in chunks, right? The same way as you watch cars go by on the highway. You could count them in dozens, right? They don't have to be in a fixed box of 12, right? Not like donuts or like eggs are packed. You could just let a dozen go by and call it a dozen, whether it happens all at once or spread out. So if you measure these coulombs that go by, right, these chunks of electrons that go by, you're talking about how much energy is delivered to each chunk. So I'm going to sort of add that down there, that voltage is measuring the energy provided to a chunk of electrons. So in a battery, for example, you have two metal plates and they're immersed in acid, and the acid rusts one, which takes the electrons off of that plate and deposits them on the other, and it ends up like unrusting this one. So inside of a battery, you're rusting one plate and unrusting the other, and that has pushed electrons from this plate to that plate, and that kind of creates a vacuum, so another electron moves in behind, and then you end up driving them in that direction. That process, the acid dissolving one metal and placing the electron on the other, is providing 1.5 joules of energy for each coulomb that goes by, because that electrochemical cell is operating at 1.5 volts. So each coulomb that goes receives 1.5 joules worth of energy that those electrons can then deposit somewhere else. And the neat thing about electricity doing transfers is that it's very efficient. There's a little bit of loss in your conductors, but unlike trying to heat something, or if you put a pot of water on top of a boiling, like on top of an oven element, and you try to boil it, the heat goes everywhere, in every which direction. It doesn't all go into the pot, which makes it terribly inefficient. But electricity tends to pick the energy up from the battery or the power source, whatever it is, and then neatly drop it on whatever your device is, which makes it really useful for engineering or powering your house, which is why you are surrounded by electrical devices everywhere. So hopefully you're able to take these two equations, the Ohm's Law and then the power expression, and understand how they're measured, why they're measured that way, and understand that amps are measuring pockets of electrons that go by every second, and that volts are measuring the amount of energy contained by one of those pockets.